Flowers led to extinction, the silent revolution in the green world. When we imagine the extinction of the dinosaurs and the end of the Mesozoic Era, the mind instinctively turns to violence. We visualize the sky splitting open, the trail of a 6-mile-wide bolide screaming through the atmosphere, and the cataclysmic impact that shattered the Earth's crust near the Yucatan Peninsula. We think of firestorms, tsunamis, and the nuclear winter that followed. It is a dramatic, cinematic conclusion to the reign of the Lizard Kings. However, there is a quieter, more insidious hypothesis lurking in the fossil record. It suggests that long before the asteroid arrived to deliver the coup de grace, the ecosystem was already undergoing a radical and chaotic transformation. This theory proposes that the dinosaurs were not just killed by a rock from space, but were slowly being destabilized, starved, and poisoned by a new biological force that had swept across the planet. That force was beauty. It was the evolution of the flower. The rise of the angiosperms, or flowering plants, constitutes one of the most profound shifts in the history of life on Earth. For tens of millions of years, the world had been dominated by gymnosperms, the non-flowering plants including conifers, cycads, and ginkgos. These plants grew slowly, reproduced via wind-blown pollen, and possessed specific chemical profiles. The animals that lived alongside them, particularly the gigantic sauropod dinosaurs, had co-evolved for millions of years to process this specific type of vegetation. Then, in the Cretaceous period, the rules changed. Flowers appeared, and with them came a biological revolution that altered the soil, the atmosphere, the insect world, and the diet of every herbivore on the planet. The question that paleobotanists and paleontologists have wrestled with is whether this floral takeover contributed to the decline of the dinosaurs, pushing them toward the brink of extinction even before the sky fell. The world before the bloom. To understand the magnitude of the angiosperm revolution, one must first understand the world that preceded it. During the Triassic and Jurassic periods, the flora of the Earth looked vastly different from a modern landscape. If a human time traveler were to step into a Jurassic forest, they would be struck by the overwhelming monotony of the greenery. There were no bright reds, purples, or yellows. There were no fruits. There was no grass. The ground was covered in ferns and horsetails. The canopy was dominated by towering conifers, relatives of modern pines, araucarias, and redwoods. Interspersed among them were the cycads, rough and palm-like plants, and the ginkgos. This was a world of slow growth. Gymnosperms generally have slower metabolic rates than modern flowering plants. They invest heavily in woody tissues and defend themselves with tough, fibrous leaves and resinous chemicals. The reproductive cycle of a gymnosperm is a leisurely affair, often taking up to 18 months between pollination and fertilization. Wind was the primary vector for reproduction. Massive clouds of pollen would drift through the prehistoric air, hoping by chance to land on a female cone. Because of this reliance on wind, these plants could not afford to be rare or isolated. They had to grow in vast, dense stands to ensure reproductive success. This structure dictated the behavior of the animals. The herbivores of the Jurassic, particularly the long-necked sauropods like Diplodocus and Brachiosaurus, were biological factories designed to process this specific type of fodder. They possessed massive fermentation vats in their guts to break down the tough cellulose and lignin of conifer needles. They did not chew their food. Their teeth were simple pegs or rakes, designed to strip branches which were then swallowed whole. The digestion process was slow, matching the slow growth of the plants. It was a stable equilibrium system that lasted for tens of millions of years. Darwin and the abominable mystery. The stability of the gymnosperm world was shattered in the Cretaceous period. The appearance of flowering plants in the fossil record is so sudden and so diverse that it famously perplexed Charles Darwin. In a letter to his friend and colleague Joseph Hooker in 1879, Darwin referred to the rapid rise of the angiosperms as an abominable mystery. He could not understand how such a complex and diverse group of plants could appear so abruptly without a clear lineage of transitional forms. While modern paleontology has found some of these transitional fossils, such as Archifructus, the speed of the takeover remains staggering. Angiosperms possessed a suite of biological innovations that allowed them to outcompete the incumbents. They developed vessels in their stems that transported water more efficiently than the tracheids of gymnosperms. They developed rapid life cycles, allowing them to grow, flower, seed, and die within a single season, whereas a cycad might take decades to reach reproductive maturity. Most importantly, they enlisted mercenaries. By evolving nectar and showy petals, flowers enticed insects to carry their pollen directly to other plants. This eliminated the reliance on wind and allowed angiosperms to exist as rare individuals scattered through a forest, or to colonize new, disturbed habitats rapidly. This was the Cretaceous terrestrial revolution. It was not just a change in scenery. It was a complete overhaul of the energy flow of the biosphere. The new plants were weedy, fast-growing, and chemically complex. The chemical arms race. The transition from a gymnosperm-dominated world to an angiosperm-dominated world was not a peaceful transition. It was a form of chemical warfare. Plants cannot run away from predators, so they fight back with chemistry. Gymnosperms defended themselves primarily with physical toughness and resins, compounds like terpenes that make pine needles taste like turpentine. The dinosaurs had millions of years to adapt to these defenses. However, angiosperms introduced a new arsenal of chemical weapons. Because they grew fast and had nutrient-rich leaves that were appealing to herbivores, they needed potent defenses. They evolved a class of chemicals called alkaloids. These are nitrogen-based compounds that have profound physiological effects on animals. Examples from the modern world include caffeine, morphine, nicotine, strychnine, and cocaine. These substances are bitter and often toxic. To a mammal with a sophisticated liver and a good sense of taste, these plants warn of their danger. But what about a dinosaur? The hypothesis put forward by some scientists, including the chaotic ideas of early molecular evolutionists, suggests that dinosaurs may not have been physiologically equipped to deal with this new toxic landscape. If a sauropod, accustomed to eating benign but tough pine needles, suddenly began consuming vast quantities of flowering plants laden with tannins and alkaloids, the results could have been disastrous. The huge fermentation chambers of the giant dinosaurs would have been particularly vulnerable. Antibacterial compounds in the plants could have wiped out the gut flora required for digestion, leading to starvation despite a full stomach. Furthermore, the accumulation of toxins could have led to liver failure or reproductive problems. The taste of death. A critical component of this hypothesis involves the sense of taste. In modern animals, the sensation of bitterness is a warning system evolved specifically to detect plant toxins. Mammals generally have a robust genetic repertoire for detecting bitter compounds. The question is whether dinosaurs possessed this genetic toolkit. Recent genetic reconstruction studies on the ancestors of birds and crocodiles, the closest living relatives of dinosaurs, suggest that the ability to taste bitterness was present, but perhaps not as refined or specific as it is in modern mammalian herbivores. If the giant dinosaurs could not taste the danger, they would have continued to browse on the encroaching green carpet of angiosperms, slowly poisoning themselves. This physiological mismatch is a classic driver of extinction in invasive species scenarios. When a new species enters an ecosystem, the natives often lack the defenses to cope with it. In the Cretaceous, the invasive species were the flowers themselves. They terraformed the planet, changing the chemical composition of the food supply faster than the giant digestion systems of the sauropods could adapt. The decline of the giants. The fossil record provides some tantalizing correlations to support the idea that the floral revolution stressed dinosaur populations. As the Cretaceous progressed and flowering plants became more dominant, the diversity of the sauropods declined in the northern hemisphere. The immense herds of the Jurassic faded away, replaced by new types of herbivores. This turnover is often attributed to the changing food source. The sauropods were essentially gymnosperm specialists. When their food source retreated to higher latitudes or was outcompeted by fast-growing angiosperms in the lowlands, the giants suffered. In their place, new dinosaur groups rose to prominence, groups that were better adapted to the new flora. These were the ornithopods, specifically the hadrosaurs, duck-billed dinosaurs, and the ceratopsians, horned dinosaurs like triceratops. Unlike the sauropods, these animals had evolved complex chewing mechanisms. Hadrosaurs possessed dental batteries consisting of hundreds of interlocking teeth that acted like grinding stones. They could pulverize the tough fibers and perhaps even process the new, more nutritious but chemically defended angiosperm foliage. However, even these successful groups may have been living on the edge. The rapid evolution of plant defenses creates a Red Queen scenario, where the herbivore must constantly evolve to detoxify the plants, while the plants evolve new toxins. It is a high-energy evolutionary sprint, the metabolic shift, and the insect connection. The influence of flowering plants extended beyond just feeding the dinosaurs. They fundamentally changed the structure of the ecosystem. Angiosperms have higher transpiration rates than gymnosperms. They pump more water from the soil into the atmosphere. This increased humidity and altered rainfall patterns, potentially creating the dense tropical rainforests that we see in the fossil record of the late Cretaceous. This warmer, wetter world favored the explosion of insect life. The relationship between insects and flowers is one of the most successful mutualisms in history. Bees, wasps, ants, and butterflies diversified alongside the plants. This surge in insect biomass provided a new food source, not for the dinosaurs, but for a different group of animals: the birds, the lizards, and crucially, the mammals. Mammals in the Mesozoic were generally small, nocturnal insectivores. The explosion of flowering plants and their associated insect pollinators provided an endless buffet for these small, furry creatures. While the dinosaurs were struggling to adapt their massive digestive systems to the new toxic flora, the mammals were thriving on the side effects of the floral revolution. This suggests that the rise of flowers prepositioned the mammals for dominance. They were metabolically faster, reproduced quicker, and were already adapting to the angiosperm world before the asteroid hit. Soil, fungi, and the nutrient cycle. The impact of the angiosperms went deep underground. The root systems of flowering plants differ significantly from those of conifers. They tend to decompose faster, creating a different type of soil profile. Gymnosperm forests tend to produce acidic, nutrient-poor soils where decomposition is slow. Think of the peat buildup in a pine forest. Angiosperm forests produce rapid turnover leaf litter, rich in bacteria and different types of fungi. This change in the nutrient cycle would have affected everything from the ground-dwelling invertebrates to the largest animals. The carbon cycle itself was accelerated. This acceleration might have added to the instability of the climate in the late Cretaceous. The world was becoming faster. The slow, lumbering energy of the Jurassic was being replaced by a high-octane, high turnover ecosystem. For dinosaurs that had evolved strategies of gigantism and slow growth, this was a fundamental disruption of their life history strategies. Evidence of pre-asteroid decline. The crucial piece of evidence for the flowers led to extinction hypothesis is the state of dinosaur diversity immediately prior to the KPG Cretaceous-Paleogene extinction event. For decades, the prevailing narrative was that dinosaurs were in their prime when the asteroid hit. However, more recent detailed statistical analyses of the fossil record suggest that dinosaur diversity was arguably in decline for the last 10 million years of the Cretaceous. Some major groups were disappearing, and speciation rates were failing to keep up with extinction rates. In North America, the number of giant herbivore species seems to have dropped. The ecosystem was becoming top-heavy, dominated by a few massive species like Triceratops and Tyrannosaurus, rather than the rich mosaic of species seen earlier. If this decline is real, what caused it? The timing correlates with the peak radiation of angiosperms. As the flowering plants reached true dominance, pushing gymnosperms into marginal habitats, the ecological niches for dinosaurs may have shrunk. The habitat fragmentation caused by the aggressive spread of weedy angiosperms could have isolated dinosaur populations, making them more vulnerable to disease and environmental stress. The flowers were squeezing them out. The counter-arguments and complexity. It is important to acknowledge the scientific pushback against this theory. Many paleontologists argue that dinosaurs were highly adaptable. The rise of the hadrosaurs and ceratopsians demonstrates that at least some lineages had successfully transitioned to the new diet. Coprolites, fossilized feces from the late Cretaceous, show that dinosaurs were indeed eating flowering plants. Some specimens contain fragments of angiosperm wood and seeds. This indicates that they were not strictly avoiding them. Furthermore, the toxin hypothesis is difficult to prove without soft tissue evidence of dinosaur livers or taste receptors. It is also possible that the decline in diversity is an illusion created by the preservation bias of the fossil record, the Senor Lips effect, where the last rare individuals of a species are never found, making it look like they went extinct earlier than they did. Moreover, the interaction was likely not one way. Dinosaurs affected the plants just as plants affected the dinosaurs. Heavy grazing by dinosaurs may have actually cleared the way for fast-growing angiosperms to take root, creating a feedback loop. The stress test and the final blow. If we accept the premise that the floral revolution placed the dinosaurian ecosystem under severe stress, the asteroid impact takes on a slightly different role. Instead of being the sole assassin, the asteroid becomes the final straw. Imagine an ecosystem that is already fragile. The herbivores are dealing with nutritional stress and chronic low-level poisoning from new plant alkaloids. The food webs are in flux due to the rapid turnover of plant species. The climate is oscillating due to volcanic activity. The Deccan traps in India were also erupting around this time, spewing gases into the atmosphere. The dinosaurs are specialized, stressed, and reduced in diversity. Then the asteroid hits. The sun is blocked. Photosynthesis shuts down. In a robust, stable ecosystem, some large animals might have scraped through. But in an ecosystem that was already teetering on the edge of a metabolic crisis caused by the shift in vegetation, the resilience was gone. The gymnosperms, the dinosaurs' traditional food source, suffered heavily in the dark, cold winter following the impact. The angiosperms, with their ability to remain dormant as seeds and regrow rapidly from rootstocks, recovered much faster when the light returned. But by then, the dinosaurs were gone. The animals that survived, The small mammals, birds, and insects were those that had co-evolved intimately with the flowers. They were the beneficiaries of the revolution. The triumph of the angiosperms. The aftermath of the extinction event confirms the victory of the flower. In the Paleocene epoch, immediately following the extinction, the world saw a brief spike in ferns, the fern spike, which is typical of a devastated landscape. But almost immediately after, the angiosperms returned with a vengeance. They formed the dense, multi-layered rainforests that define the tropics today. They conquered the grasslands, though grasses themselves evolved later in the Cenozoic. They diversified into every conceivable niche. The age of mammals is, in reality, the age of flowers. Mammals radiated into the forms we know today: horses, primates, bats, whales, largely to exploit the energy provided by angiosperm fruits, seeds, and foliage. We as humans are the ultimate result of this lineage. Our agriculture is based almost entirely on angiosperms, grains, fruits, vegetables. Our vision is tuned to see the colors of ripe fruit, a trait evolved by our primate ancestors in the floral canopy. The floral mechanism of change. Let us look deeper into the mechanics of how the flower changed the physical world. The key is leaf vein density. Angiosperm leaves have a much higher density of veins than gymnosperms. This allows them to transport water for transpiration much more efficiently. This high hydraulic capacity allows them to keep their stomata, breathing pores, open longer, absorbing more carbon dioxide and performing photosynthesis at a rate far outstripping their competitors. This high-octane growth meant that angiosperms generated biomass faster than anything that had come before. This should have been a boon for herbivores. More food, faster. But the quality of that biomass was different. It was lower in fiber but often protected by those chemical defenses mentioned earlier. The dinosaurs, particularly the large ones, were adapted to bulk browsing, eating vast quantities of low-quality food. The shift to high-quality, high-toxin food required a completely different physiological approach. It required the liver capacity to detoxify, the dental anatomy to grind cell walls to release nutrients before they pass through the gut, and the metabolic flexibility to deal with seasonal availability. Angiosperms are often seasonal, dropping their leaves or dying back. Gymnosperms are often evergreen. A non-migratory dinosaur in a gymnosperm forest has food year-round. A dinosaur in a deciduous angiosperm forest faces a season of starvation. This seasonality, introduced and amplified by the flowering plants, imposed a rhythmic stress on the ecosystem that the giants may have found difficult to navigate. The role of cryptic evolution. The evolution of the flower also drove the evolution of cryptic life. Because flowers rely on animals for pollination and seed dispersal, they encouraged the evolution of complex sensory systems. Insects needed to see UV patterns on petals. Birds needed to see red. Mammals needed to smell fruit. This sensory expansion bypassed the dinosaurs. Dinosaurs were visually oriented, but they were not the primary targets of the early angiosperm coevolutionary strategies. The flowers were talking to the beetles, the bees, and the early furry mammals. The dinosaurs were, in a sense, left out of the conversation. They were the consumers of the biomass, but they were not the partners in the reproductive cycle of the dominant vegetation. This lack of mutualism might have been a fatal flaw. Ecological networks are most robust when there are strong mutualistic ties, like the bee and the flower. The dinosaurs were increasingly becoming purely destructive exploiters of a system that didn't need them. In contrast, the mammals were becoming essential partners to the plants. When the crash came, the partners saved each other. The exploiters perished. The geological perspective. Geologically, the breakdown of the supercontinents Gondwana and Laurasia occurred throughout the Cretaceous. This rifting created more coastlines and separated land masses, which usually increases diversity through isolation. However, it also aided the spread of angiosperms. As continents drifted apart, the hardy, weed-like ancestors of flowers could cross water barriers via birds or floating debris more easily than heavy gymnosperm seeds. They colonized every island and continent. The homogenization of the world's flora began. We see the same plant families appearing in North America, Europe, and Asia. This global dominance meant that there was no refuge for the gymnosperm-dependent fauna. Everywhere they went, the green prison of conifers was being replaced by the flowering garden. The consistency of this biotic pressure across the globe supports the idea that it was a worldwide stressor, not a local anomaly. The psychological landscape of the dinosaur. We rarely consider the behavioral psychology of extinct animals, but the floral revolution would have demanded behavioral plasticity. For a herd of triceratops, the landscape was a shifting mosaic of food and poison. Learning what to eat and what to avoid would have become a critical survival skill, passed down from parent to offspring. If the flora changed too fast, faster than cultural transmission or genetic instinct could keep up, nutritional errors would occur. We see this in modern livestock. Cattle will eat poisonous weeds if they are moved to a new pasture they don't understand. Did we see a widespread collapse in instinctual herbivory among dinosaurs? The fossil record cannot show us a stomachache, but it can show us stress bands in teeth and bones. Paleopathologists have found evidence of disease and developmental stress in late Cretaceous dinosaur bones. While often attributed to climate or population crowding, nutritional stress caused by biotic upheaval is a valid interpretation. The legacy of the hypothesis. The theory that flowers led to extinction is not a claim that a petunia strangled a T-Rex. It is a sophisticated ecological argument about the fragility of food webs. It highlights that extinction is rarely a single-cause event. It is usually a 1-2 punch. The biotic turnover weakened the knees of the giants, and the asteroid delivered the knockout. This perspective makes the study of the Cretaceous much more relevant to the modern world. We are currently living through another massive shift in global flora and fauna, driven by human activity and invasive species. We are changing the chemistry of the atmosphere and the soil. We are seeing the collapse of specialist species and the rise of generalists. The story of the dinosaur and the flower is a cautionary tale about the consequences of rapid ecological change. It teaches us that even the most dominant, massive, and seemingly invincible organisms can be brought low if the foundation of their world, the very plants they eat, shifts beneath their feet. The unanswered questions. Despite the compelling narrative, much remains unknown. We do not know the exact toxicity levels of Cretaceous angiosperms. We do not know the precise gut chemistry of a titanosaur. We are relying on proxies and modern analogs. Future research using isotopic analysis of teeth, more detailed coprolite studies, and advanced genetic modeling of dinosaur ancestors will shed more light on this. We may find that some dinosaurs were adapting quite well. We may find that the decline was regionally specific. But the correlation remains. The world turned to flowers and the dinosaurs died. The coincidence is too great to ignore. The final synthesis. In the grand scope of deep time, the victory of the angiosperms is the most significant event since the colonization of land. They brought color, scent, and complex chemistry to a monochrome world. They built the modern biosphere, but the price of this revolution was high. It demanded the removal of the old guard. The gymnosperm forests and their gargantuan guardians had to fall to make way for the high-energy, fast-paced world of the Cenozoic. The dinosaur, for all its majesty, was a creature of the conifer age. It was an analog giant in a digital world. When the flowers bloomed, they signaled the end of an era. The petals that opened in the Cretaceous sun were not just reproductive organs. They were the flags of a new empire, an empire that had no room for the slow, the giant, and the inflexible. The asteroid was the executioner, but the flower may well have passed the sentence. Thus, when we look at a blooming rose or a field of wheat, we should see not just beauty or sustenance, but the relentless power of biological innovation, a power capable of toppling giants. The physiological mismatch detail. To further expand on the physiological mismatch, we must look at the fermentation process. Sauropods were likely hindgut fermenters. This means they swallowed food into a massive chamber where bacteria broke it down. This is a system based on volume. You fill the tank and you wait. It works best with fibrous, low-nutrient food that stays in the system for a long time. Angiosperms, however, are often lower in fiber and higher in sugars and starches. If you put high-sugar food into a slow fermentation tank, you get acidosis. The bacteria produce too much acid too quickly. This is a condition known in modern horses and cattle as bloat or grain overload. It can be fatal. It causes gas buildup, colic, and metabolic acidosis. If the angiosperms were taking over, and the sauropods were forced to eat this lush green, watery fodder instead of dry, fibrous needles, they might have suffered from chronic acidosis. Their massive guts, evolved for a different era, turned against them. They would have felt full but been metabolically sick. This internal dysbiosis would reduce their growth rates, lower their clutch sizes for eggs, and make them sluggish and vulnerable to predators. It is a slow, agonizing way for a lineage to die, contrasting sharply with the sudden violence of the impact theory. The rise of the weed paradigm. We must also consider the structural nature of the vegetation. Gymnosperm forests are open and park-like, or dense and dark. Angiosperms create chaos. They create thickets, brambles, vines, and dense undergrowth. This physical restructuring of the environment changes predator-prey dynamics. A Tyrannosaurus rex is a large animal. It needs space to move. If the undergrowth becomes a tangled web of vines and briars, the ancestors of grapes and berries, movement becomes more energy expensive. The line of sight is reduced. Ambush predators might benefit, but large pursuit predators would struggle. Conversely, smaller animals, the ancestors of raptors and small mammals, would find protection in this dense, chaotic foliage. The physical architecture of the flower world favored the small and agile over the large and lumbering. This structural argument adds another layer to the death by flower hypothesis. It wasn't just the chemistry. It was the architecture of the forest itself that became hostile to gigantism, the co-extinction of specialists. Ecology teaches us about co-extinction. When one species dies, those dependent on it also die. But the reverse is also true. When a species succeeds, it pushes out those who cannot use it. The insects that radiated with the flowers were specialists. The bees, the lepidopterans, moths and butterflies. They ignored the gymnosperms. The insect fauna of the Jurassic was different, dominated by beetles and flies that fed on detritus or gymnosperm pollen. As the insect population shifted toward those that serviced angiosperms, the insectivorous dinosaurs, and there were many, had to adapt. If the new insects were flying faster or living in different microhabitats or possessed warning colors and toxins of their own sequestered from the plants, the food web for small dinosaurs would also be disrupted. The entire trophic cascade, from the sunlight hitting the leaf to the predator eating the herbivore, was rewritten. The climate feedback loop. Let us return to the climate. Angiosperms, with their broad leaves, have a lower albedo, reflectivity, than needle-leaf forests in some contexts, but they also transpire more. This creates a complex climate feedback. The angiosperm climate is generally wetter and more buffered. However, the transition period would have been unstable. As the gymnosperm forests retreated, the carbon sequestration rates changed. Gymnosperms are excellent at locking carbon into wood and soil for centuries. Angiosperms cycle it faster. This release of carbon, combined with the Deccan Traps volcanism, likely contributed to the greenhouse spike at the end of the Cretaceous. Dinosaurs were thermoregulators, possibly mesotherms, somewhere between cold and warm-blooded. They were sensitive to heat stress. If the world got hotter and more humid due to the combined effects of volcanism and the new biological pumps of the angiosperm forests, the thermal window for a 50-ton animal might have closed. Large animals have trouble dumping excess heat. A hotter, humid world is a dangerous place for a giant. The role of fire. Fire is another factor. Gymnosperms are flammable resins, but they are adapted to fire regimes that clear the understory. Angiosperms, particularly the early weedy kinds, create a different fuel load. They create continuous fuel ladders. The fire regimes of the late Cretaceous may have intensified, leading to more frequent, intense burns that disrupted the nesting grounds of dinosaurs. Dinosaurs laid eggs on the ground. A fire-prone world is harsh for ground nesters. While birds, avian dinosaurs, could fly away and mammals could burrow, the large non-avian dinosaurs and their nests were vulnerable to the changing fire ecology brought about by the new plant biomass. The final verdict of the fossil record. Ultimately, the fossil record tells a story of replacement. We see the spores of ferns, then the pollen of gymnosperms, and then, inexorably, the pollen of angiosperms rising to constitute 60, 70, then 80% of the assemblage. Paralleling this curve, we see the decline of the stegosaurs, the sauropods, and the rise and subsequent struggle of the hadrosaurs. The lines on the graph cross. The correlation is there. While correlation is not causation, in ecology, distinct correlations usually point to a functional relationship. The flower did not hate the dinosaur. It simply outpaced it. It invented a faster way of living, a more complex way of defending itself, and a more efficient way of reproducing. The dinosaur, a masterpiece of biological engineering from a slower time, found itself in a world that was moving too fast. The asteroid ended the game, but the flowers had already changed the rules. The ongoing research into this field is vibrant. Paleobotanists are finding older and older angiosperms, pushing the timeline back, trying to see if the fuse was lit even earlier in the Jurassic. Geochemists are looking at the isotopic signatures of dinosaur teeth to see if they can detect the shift in diet from C3 plants, gymnosperms/primitive angiosperms, and the stress markers of malnutrition. As our resolution of the past improves, the murder in the Cretaceous mystery becomes less of a whodunit and more of a tragedy of obsolescence. The dinosaurs were not failures. They were simply characters in a play that had run its course, pushed off the stage by the changing scenery. The flowers were the new set design, and they demanded a new cast of actors. We, the mammals, were that cast. And so, in a very real sense, we owe our existence to the bloom. The extinction of the dinosaurs was the necessary condition for our rise, and the flower was the agent of change that prepared the world for us. Modern implications. The study of this ancient transition also informs our understanding of biodiversity today. We observe that monocultures are fragile. The gymnosperm forests were, in a way, monocultures of limited diversity compared to the angiosperm rainforests. When diversity exploded with the flowers, it created a more robust system, but one that required high-energy inputs. Today, as we reduce biodiversity through habitat destruction, we are reversing the engine. We are simplifying the world. The lesson of the Cretaceous is that complex, diverse ecosystems are resilient, but the transition from one state to another is often catastrophic for the incumbents. We are the incumbents now. The plants are still changing, adapting to the new climate we are creating. The question is whether we, like the dinosaurs, will find ourselves physiologically and socially unsuited for the world that is coming, or if we, like the early mammals, will find a way to adapt to the new bloom. Conclusion: flowers led to extinction not through malice, but through the sheer unstoppable force of evolutionary superiority. They reshaped the energy dynamics of the planet. They altered the diet of the giants. They changed the soil, the air, and the fire regimes. They invited a new army of insects and supported a new class of small, warm-blooded opportunists. They created a world that was hostile to the specific biological requirements of the sauropods and their kin. The asteroid was the final, violent punctuation mark at the end of a long sentence of decline, but the sentence was written by the flowers. The petals that color our gardens today are the descendants of the revolutionaries that brought down the kings of the Mesozoic. It is a sobering and beautiful thought that the softest, most fragile things on Earth, the flowers, could possess the power to overthrow the strongest. This is the true science of the Cretaceous, the triumph of metabolic efficiency and coevolution over brute size and static defense. The flowers won. The dinosaurs lost. And in the garden of the Cenozoic, the survivors thrived.